Hi everyone, and welcome to the video on sections 3.6 and 3.7. So these are combined because they are two sections where we get to learn a few more derivatives to add to our toolbox. And the way we get these is, for both of them, is using section 3.5, the implicit differentiation. So they just pretty naturally go together. So the first section, 3.6, is about inverse trig functions. So this is stuff like arc sine, arc cosine, arctan, those, which, just as a reminder, we write these two different ways. So this is a way, or you'll see this. So both you'll see, both I'll do, just you gotta be thinking about this. So just as a little side note, these mean the same thing. Okay, so we have to just remember a little bit about inverse functions in general and what these inverse trig functions look like, because they're a little bit different than other inverse functions we've seen. So looking at this first picture, we see sine. So this is sine x. Now remember, what's an inverse function? An inverse function is something that if sine is taking an x value and sending it to a y value using sine, then the inverse of sine, right, arc sine, or sine inverse, will take in a y and bring it back over to an x. That's the way we can think about this. Okay. So, okay, you're thinking like, all right, fine. There's a problem with this though, and the problem is, just try it. Pick a y value. So we're going to pick the y value 1. So, okay, let's pick a y value to send backwards. All right, so what's the point of sine inverse? Sine inverse says that you gave me this y value. Now all you have to do is give me an x value, right, such that sine of that x hits 1. So let's actually just kind of draw this 1 here. So the whole goal is you give me an x value that hits this y value. And the problem is, some of you were just like, here, there you go, there's an x, because this is the function sine. But other people were probably like, ooh, this one. And then maybe some other people trying to be, all fancy, were like, over here, there's another one. This continues over here. I'm going to hit it again. So that's a problem, right? A function, is something where if we plug in the same thing, we're supposed to get the same thing out. So that's really bad. So this is not one-to-one. That's the, our fancy math term. This is not a one-to-one function sine because it hits the same y value multiple times. It hits 1 infinite number of times. It hits 0.5 infinite number of times. So you can't just take one of those y's and tell me what the x is that sine maps to it. It doesn't work because there's too many. This needs to be just one-to-one. So what we do to get around this, because we still want to understand an inverse function, like have that idea, what we do is we say, okay, can I just find a place where it is one-to-one? So let's just start with this point here, right? If we want this 1 to go back to only one x value, then we need to make sure we can include over here. So we somehow have to restrict down the sine function to not have both of these peaks or both of these valleys, right? We can't have that. And the general pick is to actually slice at those kind of, maybe not necessarily important, but the more kind of obvious parts to this curve, the top and the bottom. So the idea is just restrict down to go from one valley to one top, right? Just between the blue. So focus only on sine between the blue, and then ask yourself the question, pick any y value between -1 and 1. How many times does sine hit that y value in just this, in between these blue lines? So if you think about this, it hits -1 once. Okay, it's hitting all these y values, hits 0, hitting all these positive y values, hits 1, but it never hits any of those y values more than once, right? We've done a good job. We've sliced sine. Whew. So what we do then is we say this. We say, okay, I want to get a function sine inverse. Well, how do I do that? Well, what we say is we restrict y equals sine x to x being only between negative pi over 2 and pi over 2. Or if you're more comfortable with this notation, I'm just saying the same thing here. X is between these two only. Then, this is okay. If we restrict sine here, then we can talk about the function. And we're going to write this a couple different ways, but just to kind of keep nailing home this inverse idea. We can talk about this function where y will go between negative 1 and 1. That's what I'm allowed to plug in, because I have to plug in something sine actually gets to. I can't plug in 2 because sine never gets to 2. So it's got to be something in the range of sine. And what I will get out then is an x between pi over 2 and negative pi over 2. Okay. So what's a little bit confusing sometimes about these is, like, I think this isn't too bad to go through, but then the thing that can be a little confusing is we generally want to be able to talk about functions where y and x are not like this. They're flipped, right? We almost always are like y is a function of x. So I want to talk about sine inverse like this. Y equals sine inverse x. And it's, you know, this is a nice way to write it because I think it does a good job kind of showing you this, okay, sine takes x, it produces y. So sine inverse produces, you know, an x from a y. It's kind of backwards. But we generally, when we're talking about sine inverse, we still want to keep x as the input, y as the output, just because we're so used to that. So in that case, we just have to flip this around a little bit. The x values that it can take in are negative 1 to 1, and the y values it will produce then are pi over 2 to negative pi over 2. Don't overthink here to here. It's just me switching the variables, that's it, so that I can talk about inputting x's and outputting y's, because that's how we treat most of our functions. And so then you should graph this. You should immediately, you see a new function, you should graph it. It's going to go from negative 1 to 1, okay? And then you got to kind of think about this, right? It's not too bad to do this. Plug negative 1 into here. You're asking the question, what value goes into sine in order to get negative 1? So let's just write that down, because that's a lot to say. Sine inverse of negative 1. I give you that. This is me asking the question, what x, or you can think of this as a y. So what number do I plug in to sine, so sine of this number, such that I get negative 1? That's the whole point of the inverse, right? This is exactly the answer to this question. What number, when I plug it into sine, gives me negative 1? And so you can use this, you can use the unit circle if you want, right? You know, that's all fine. So you could be sitting here with your unit circle, like, okay, negative 1, here's the unit circle, right? Well, so, okay, so pi over 2 would be up here. Now, here's where you got to be tricky. If I'm going this way, right, that's 3 pi over 2, but that's not part of what I'm talking about. We are talking about, if you want to use the unit circle, these are the angles that we're talking about here, right? We're talking about all of this. So the angles 0 up to pi over 2, and then 0 down to negative pi over 2. These are the angles that we're considering for this function. So to get down to negative 1, I'm at negative pi over 2, which maybe is right here. Okay, and then now we got to start thinking, all right, well, just do, a simple one. 0. What's sine inverse of 0 going to be? Well, what do I have to plug into sine to get 0? Oh, 0. So I'm going to hit here. And then we go up to 1. That's pi over 2. and you end up getting a function that looks something like this, approximately. Okay, so that's what sine inverse looks like. All right, so we have a function, looks like a function. Okay, not bad. We can graph this, play around with plugging things in so you can get used to it. But we're in chapter 3, so we got to get a derivative. So here's the function. I want a derivative. And just kind of quickly looking at this graph, pick a point. I should be able to draw a tangent line here. I think that I should be able to do a derivative. So I think hopefully it's not too bad, this whole curve to see, yep, we should be able to do a derivative this whole way. Okay. So how do we do the derivative? Well, the way we do a derivative here is we actually use implicit differentiation. So let's actually do that down here. I think I left space on the next page, but that's fine. So y equals sine inverse x. All right, so here's the trick. Sine inverse, blah. I don't like it. I like sine better. Okay, so we're going to take the sine of both sides. Okay. Now, the sine inverse, because by just writing this down, we've restricted, right? Just the fact that I've written this down has restricted x between -1 and 1, which we know the y will then be between pi over 2 and negative pi over 2. So that's, if I write this equation down, it's implied that I'm saying the x values are restricted, and so then these are the y values that can come out of this. Okay, so with that done, I'm fine taking sine of both sides because it will be defined. Sine inverse, this is going to cancel, and it gives me this. Oh, I could deal with sine. That's not too bad. I have implicit differentiation. I can do the derivative of both sides here. This looks like just like it could have been a problem from the last section. So derivative of sine is cosine. Don't forget your y prime, this is chain rule, implicit, equals 1. So y prime equals 1 over cos y. Hooray! Except y equals arc sine x, sine inverse x. This is a function in terms of x's. I kind of want my derivative in terms of x's. So while this is, pretty good, this is fine, it's better to have things in terms of x. So then there's a little more work with these in figuring out what this is in terms of x's. Okay? But it actually isn't too bad. We have some trickiness with this. That's, this is a big thing to remember. Sine squared, right, plus cos squared equals 1. So then cos squared equals 1 minus sine squared. Okay, and then if we square root, we end up with cos y equals root 1 minus sine squared y. Now, you should stop me here and say, whoa. This is a plus or minus. What are you doing here? But remember how we restricted this, right? Y is between negative pi over 2 and pi over 2. Go back to your unit circle we drew up here. We're over here in these angles. Cosine is always either 0 or positive with these values. So I know cosine's either 0 or positive, so I actually can just stick with this because, just to remind you again, we said y had to be between negative pi over 2 and pi over 2. So, okay, cool. Cosine is now in terms of this. Great. So you're probably like, you made things worse. All right, okay, you're right. That doesn't look better. But sine of y is just x. We did that up here, right? Sine y is just x. So this is square root 1 minus x squared. Put that together, and you get y prime equals 1 over square root 1 minus x squared. Ta-da! And there you go. So a little tricky, especially this last piece, but hopefully overall each piece itself isn't too bad with what we've learned so far. And, this doesn't have to be something, that you're going to replicate necessarily on a test. Just this has to go in your toolbox. Put this in your toolbox. The derivative of arc sine, or sine inverse, is this. Just toolbox. Okay? All right, so let's try some more examples. Now, again, definitely check out arctan. Look over how to do this. Try it yourself. Not a bad idea at all. Make sure you know what this graph looks like. Make sure you know what values we can plug into this, right? So lots of things to kind of think about here. But when we get to just doing the derivative piece, it's not too terrible. We can just kind of follow our rules. So how do I do this derivative? Well, I see chain rule. So this is a chain rule. So then my two functions are arctan, and the inside is going to be x squared. All right, so putting this in our toolbox, 1 over 1 plus x squared. Derivative here, g prime is 2x. And then, I know how to do this. So the derivative of this would be f prime, 1 over 1 plus, but then careful, not just the x here, right? I need to take x squared into this. So that'll be x to the 4th times the derivative of the inside, 2x. Done. Boom. So, trig is so scary. Not really. Just do the things you know how to do. Put this in your head. You know how to do the chain rule. Just do it. Done. All right, let's try another one. Okay, now this one has lots of signs in it. This one must be harder. We'll see. So again, I see chain rule. F is arc sine theta. Again, just you see theta, use theta here. G is what's inside here, square root sine theta. Okay, so I see what they're doing here, right? This G is actually also a chain rule, right? So, maybe over here we can do that off to the side. You don't have to do things off to the side like this, but if you want to. So then this is actually what? Sine theta to the 1/2 power. So the derivative will be the derivative of the outside. Plug back in your sine. 1/2 times the derivative of the inside, which is cosine. So, okay, we got that. So g prime is 1/2 cos theta root sine theta. Our f prime is, well, we just did this one, so that's not too bad. 1 over root 1 minus theta squared. Again, I'm just theta because that's what we're using here. Okay, so chain rule on this. F prime, 1 over, so big F prime will be 1 over, and then we'll do the square root 1 minus, now again, not just theta squared, whatever the inside was. So this is going to be square root sine theta squared, okay? And then multiply by what? The derivative of the inside. This was the inside, this was its derivative. 1/2 cos theta, and then what do we have here? Square root sine theta. Okay, so hopefully that's not too bad. Get through and go through that. Move stuff around, try to do a little simplification algebraically here, but altogether that's not too terrible. Just break it down piece by piece. You can do that. Okay, so the last thing is actually this 3.7, and this is all about log functions, and we can use implicit differentiation here as well. So, what do we mean by that? Well, y equals log x. I want the derivative. What's y prime? Well, just like looking at this, I don't know. This looks like it should just have a rule, right? Because it's just one function. So yeah, well, we can make that rule, and here's how we're going to do it. It's very similar to how we just attacked the arc sine problem. we're going to do e to the y equals e to the ln x, which this is such a common trick to do. Keep this in your brain for later. The whole point of that, though, was to get the x by itself. Okay. Now we are in this situation where we've got an equation with y's and x's, and there's, it's all kind of mangled together. So then we can use implicit differentiation here to do this. All right, so then that's going to be, well, derivative of e to the y is e to the y, but this is technically chain rule. Y is a function of x times y prime equals 1. Y prime is 1 over e to the y. But what was e to the y? E to the y was just x. There you go. So hopefully that's not too bad to do. There you go. We now have a new rule. Y prime, so what's our new rule? The derivative of ln x is 1 over x. Woohoo! So, hopefully that's not, the worst thing in the world to be like, okay, cool. And we just have to now keep that in our head. So, let's try an example. Having this new rule. Again, I see chain rule. F is natural log. G is sine squared. Okay, derivative of f, we just did that. That's 1 over x. Derivative of sine squared. Okay, actually, this is chain rule 2, but this is one of those chain rules that's a little bit simpler, right? Get out of here. Because it's just a function to a power. We talked about how to do this as a little kind of shortcut. Just drop the power, right? Put it in 1 here, multiply by the derivative of the inside, which is, again, sine. So that would just be cosine. There you go. So, chain rule. Derivative of the outside, log 1 over, plug back in the inside, sine squared x, times derivative of the inside, sine x cos x. Okay, we get some cancellation here. That's pretty easy to do. So, f of x prime of x. Well, I guess I abuse notation calling this f here. We'll make this one a fancy f with some eyeballs. There you go. So this is clearly a different function. Maybe it's got some feet. Look at me go. Going off the rails here a little. But that's fine. So there you go. Clearly, I did not abuse notation now. So this is going to end up being 2 cos x over sine x, which equals 2 cotangent x. Boom. You know how to do them. Just do them. Okay, getting down here, let's try this next one. So again, to me this looks like an inside and an outside function. So just to rewrite this to make it a little easier to see, this is natural log of x to the 1/5 power. So then the derivative of this, again, this is chain rule, but this is one of those quicker ones. 1/5 ln x to the -4/5, because remember I subtract 1, times the derivative of the inside, 1 over x. All right, all done. Boom. Chain rule, but it's a function to a power, so the chain rule is a little easier to do. Drop it, subtract 1, multiply by the derivative of the inside. Okay, with this one, I again see an inside and an outside. I see for my first function, f of x will be x squared, because it's the square, that's the most outside thing. The inside here will be natural log of 1 plus e to the x. Okay, this one though has its own separate chain rule, right? So the outside, which we'll call O, is natural log. The inside function is 1 plus e to the x. Okay, so O prime is 1 over x. I prime is e to the x. And so we know how to do chain rule here. Derivative of the outside is 1 over, plug back in, times the derivative of the inside. So that's going to be altogether our g prime. F prime, on the other hand, is just 2x. So the overall big chain rule this big f and g was derivative of f is 2 times, plug back in, 1 plus e to the x, times the derivative of the inside, which we found out was this, e to the x over 1 plus e to the x. And done. You get your rules down, these problems, they go quick. They're just, I have practiced enough, I see chain rule. I've practiced enough, I know x squared 2x, boom. I practiced enough, derivative of 1 plus e to the x, oh, derivative of 1 is 0, e to the x, go. That's where you got to get to, right? But then hopefully these, aren't too bad to get through as you practice more and more, but you just got to keep practicing. So, okay, so we've got now a even larger toolbox. We've got inverse trig functions, we've got log functions, we've got a ton, so tons and tons of functions that we can take derivatives of, right? And so what we'll be moving on to is how do we do some, how do we use these? How do we use these to solve problems? So chapter 4 is going to get into things like related rates, using this to find mins and maxes. We still have 3.9, which is linearization, which is seemingly kind of like silly and doesn't seem like much, but is actually a really big and cool idea. So that'll be coming up soon. But for now, you just getting ready for this test. Practice these. If you need help with any of them, of course, let me know. Don't forget, you've got Mathematica that can handle these derivatives as well to help you out. Just as a word of warning, though, if you use Mathematica or Wolfram Alpha or any of these things, they might do algebra at the end of a problem that makes their answer seem different than yours. Maybe they simplify, maybe they don't. So before you just assume you're wrong with what answer they give or your answer's different, try to think a little bit algebraically whether or not these two things that you are seeing are the same. That can happen, so just try to be aware of that. Otherwise, let me know if you have any questions, and I'll see you in the next video.